Hello everyone, welcome today to Mike's SAS Tutorials. This is lesson 8, and I'm going to be talking today about the two-sample t-test and the paired t-test. I'm going to be using the examples that come out of the SAS help manual, and to get to that, to see those examples, all you have to do is go to the SAS help manual, click on search, type t-test, and then scroll down to where it says the t-test procedure, and then you'll see the table of contents here, and I'm going to be showing this example right here, comparing group means for the two-sample t-test, and this example down here for the paired comparisons, the paired t-test. I'm going to start actually with the paired t-test because I feel like it's a little bit more intuitive. Um, the idea behind the paired t-test is basically when you're going to compare measurements from a single source. In other words, if you're taking a before and after measurement from the same subjects, or if you're measuring some change in a machine between one time point and another, as long as it's on the same subject, the data that you measure from it is always going to be dependent on that same subject. So I'm going to use this data pressure that's given right here that talks about the blood pressure, the systolic blood pressure of 12 men from a study where they were given some kind of stimulus. So to start with, just go ahead and copy that data and paste it into SAS, and I've done that for you here. And I gave this note here that the data is paired because the measures are dependent on the subject. These 12 men are where the systolic blood pressure was measured before and after given this stimulus. So if you run this data and then scroll down here with me, the t-test procedure is actually really simple to do for paired data. All you have to do is type in this paired statement, the first measure, and then this asterisk, and the second measure. Now the thing that's really nice about this is you can see without doing any like fancy graphics, it's really easy coding. You just specify the data set, the before measure, the after measure, and you select it and run. Now when you see the output, you're going to have only one folder and these three parts here. And in fact, all three parts are given to you right away in this short little summary. And the most important part is obviously the t-value, the degrees of freedom, and the p-value here. Now you have to ask yourself when you're looking at any p-value, what is the null hypothesis? Well, the null hypothesis for a paired t-test is that the means on the before and after measurements, or whatever the two paired variables are, the mean of those two variables are equal. And so in this case, we want to show that this stimulus doesn't change the systolic blood pressure of these 12 men. And when you see that the p-value is not less than 0.05, which is our default alpha value, our p-limit, if you want to think of it that way, then you can say that we would fail to reject the value. We would fail to reject the null hypothesis. So in this case, if we fail to reject the null hypothesis that the means of the before and after systolic blood pressures are different, then what we conclude is that they are not different. In other words, the stimulus does not change the systolic blood pressure within these 12 men. So that's all well and good, but we also want to make sure that we can properly use the t-test. Now remember that the t-test is a parametric test statistic, and so we have to make sure that we are not violating the assumption of normality. So to do that, to confirm that we're not doing that, you want to use these graphic options. As I showed you last time, you can use a QQ plot or a visualization of the histogram to make sure that you are not violating those assumptions. So my computer is taking a second here to load it. Hopefully it's going to be okay. Okay, so it seems to have worked. The log seems to not show any errors. The results have populated here. And if you zoom in, you can see that it's given you 1, 2, 3, 4 new graphics. Now this summary panel is what you would see from last time. It's basically plotted out the histogram of the data, given you what the normal distribution plot would look like, and it's given you this kernel density plot. And you can see that the data seems to be pretty normal, but we want to make sure that the QQ plot doesn't show any obvious deviations. And here you can see that it seems to be all right. I mean, the data is basically hovering around this one line, and it seems to be okay. Now, from last time, if you remember, there's one other thing you could do to make absolute sure that your variables are normal, and that is you can use the PROC univariate procedure. Let's do it on this data pressure. We're going to do it on variable systolic blood pressure before and also systolic blood pressure after. I'm going to type histogram slash normal, and that slash normal part is what's going to give us the tests for normality. If you remember from lesson 7, the test for normality that I use is the Anderson-Darling test, and the basic null hypothesis of that test is that the data is normally distributed, so we don't want to reject that null hypothesis. If I run this, I can see the, let me zoom in here for you guys, the two folders for each variable. I'm going to look at the before variable first, under histogram, normal fit, and then goodness of fit measures. And here we can see the Anderson-Darling test is here, and the p-value is not less than 0.05, so we're good to go. We can be certain that that variable, that before variable, was normally distributed. And if I do the same thing for our after variable, you can see here again that the p-value is not less than 0.05, so we're good to go. So it was good for us to use the pair t-test, and because we were able to find the p-value from it, we saw that the means of the two groups, the before and after groups on these men, were not different, so the stimulus doesn't seem to change the systolic blood pressure. That's pretty much all there is to doing a pair t-test. But remember, you always want to use a pair t-test in the correct setting, so you want to use it when you have dependent data or data measured on the same subject. Now you might be asking yourself, what about if I have independent data? I have data from two different subjects. For example, if we had some scores on some test for males and females, and we want to see are there any gender differences. So in this example, this of course comes from the SAS help manual again. I'm going to go back. I'll show you, here's the table of contents from the t-test procedure in the SAS help manual. I'm going to go here to this comparing group means option, and I'm going to show you the example that the SAS Institute has provided for you in their help manual. So in this example, they get golf scores for males and females in a physical education class. The sample sizes from each population are equal, but is not required for further analysis. The scores are thought to be approximately normally distributed within gender. And of course, if we wanted to test that, we could, again, using our univariate procedure. So here I'm going to just run the data, and just to keep everything clean, I'm going to delete the results here so that we have a nice fresh start. I'm going to clear the log so we don't have any previous log errors to look at, and I'm just going to close this graph window that came out of the univariate procedure. Now I note here that this is independent data because the measures are from different subjects. In other words, when you have different measurements that are not measured on the same subject, they're measured from different subjects, then the data is independent of every other subject and is therefore not related to each other. If it were related to each other, remember we would use our pair t-test. As such, this is a two-sample test. The two-sample basically means that some measurements are coming from one source, other measurements are coming from a second source. And in that case, you would use a two-sample t-test. So here I show again without the graphics. You can see that the t-test procedure now has this new line, this class statement, and everything else seems to be something we've seen in the last example where we had var statement and the variable that we're trying to assess. So the thing about the class statement, and the class statement is used actually in a lot of procedures, it basically breaks up the data into different values of the variable, the class variable that you include. So here the class variable is gender. Our variable score now is going to have some values for males and other values for females. And to show you what I'm saying by that, if you go ahead and look under the work directory, the work library, and you look at the scores data, you can see that there's female scores and male scores. In fact, let me zoom in on this. Here you see that the females have some scores and the males have some scores. So this class statement is basically going to break it up or stratify the subjects into two different groups that we're going to analyze here. So let's close this, making sure always to close the data before you run any procedures on it, and then go ahead and run this PROC t-test. Now, one thing you're going to notice right off the bat is first off, the table of contents here, or the tree structure of the results, is slightly larger than it used to be. And we've also got this equality of variances line that we haven't seen before. So let's go ahead and look at the overall picture of the results. This is it. And we can see here now what it's done is it's given us separate descriptive statistics for each class row. And in this case, there's only two. There's the females and the males. And it's showing us that in each case, there's only 7 subjects. And it's giving us the independent mean for that group. So for females, the mean golf score was 76.8571. And for males, it was 82.7143. Here's the standard deviation, the standard error, the minimum, maximum. All of this is what I classify as descriptive statistics. It's describing, in this case, these two populations, the population of females and the population of males. Now, the other thing it's doing here is it's giving us a difference. It's saying one group minus the second. So females minus males, the mean was, if you were to basically subtract every row, then you're going to have a average difference of negative 5.85. In other words, males have scored higher than females. But we want to make sure that that's a true statement in the greater population, not just our sample. So the thing we have to do before we make any kind of conclusion at all, is we have to make sure that the variances are equal. Now this is an assumption for the two-sample t-test, and that is that we're going to have to use different methods of the two-sample t-test based on whether or not the variances of the two groups are equal. So the equality of variances test that's provided here, it's using this folded F method, is going to have a null hypothesis that the variances are equal. So in other words, if we were to have a p-value that was less than 0.05, then we would conclude that the variances are not equal. But in this case, it's greater than 0.05, and so we conclude that the equality of variances is true. In other words, the variances of male and female scores is similar, it's equal. So in that case, we would look here now at this pooled t-test method, because it's saying that the variances are equal. And now we have a p-value here that we can make conclusions on. And so the conclusion here, since the p-value is much less than 0.05, and remember 0.05 is just a relative alpha limit that you can specify, in other words, in 5% of the cases. So basically we're saying here that we can conclude that there is a difference in golf scores between males and females. So it really depends on whether or not this equality of variances is met. So in this case, the variances are equal. We use the pooled variances method. However, if they were unequal, we would have to use either this Scatterthwaite method or the Cochrane method. And you would have to look up the pros and cons of each method before deciding whether or not it would work for your data. I've been taught it's better to use the Cochrane method, and so by default, in fact, let me zoom out here, I include this Cochrane line, which gives us our Cochrane method p-value. But in other cases, you may not use the Cochrane, and it would be best to just look it up online or in your textbook to see which unequal variances t-test method you would be using. But since that's not really the case here, we do have equal variances, we can use the pooled method and not have to worry about it at all. So the conclusion we draw is that the differences in means between males and females exists. One last thing I want to show is how you can get the graphics on a two-sample test. Again, all you have to do is include this ODS graphics on and ODS graphics off around the PROC t-test. One thing I want to also clarify is that you can sometimes leave this ODS graphics off out. And if you just leave it as this, the first time SAS runs into this line, it's going to keep the ODS graphics on for all procedures you run thereon. So if you want to keep your ODS graphics on for the duration that you're using SAS that day, you can, But sometimes, as you saw in my case, I mean, my computer is kind of powerful, but sometimes it can make your procedures a lot slower to run, and it could take a lot longer to get your results. So just to show you one quick example of what the graphics look like for a two-sample t-test, I'm going to zoom in here and show you the tree structure. We get now a really cool looking picture of both populations. Here's the distribution or the histogram for the females, and here's the you can see here this F is very small. In fact, let me zoom in. Oops. You can see the F right there for females and the M right here for males, and those are the distributions for each. There's this little nice box plot down here on the bottom, and it's actually really clever how SAS does some of these pictures, because in the past it used to be something you'd have to spend hours to create. You can also then look at the QQ plot, and again they show it for the two different samples, here for the females and here for the males, and you can see that for the most part normality seems to be met because the points are falling pretty much on that line. There's this one point right here, it seems to be a little off. You might ask yourself, why is that? And here the points are all seeming to fall around the line. Again, just as before, if you want to do a formal test for normality, you can do the univariate procedure on each variable. So here we want to do it on score, and we want to run it. But remember that we don't have male scores and female scores as separate variables, so we have to use this class option on the gender to get separate univariate statistics for the two scores. Oops, one last thing, sorry. Histogram / normal to get our normality tests, and if I run that, you can see the histogram. Let me zoom in here for you. For females, normal fit, goodness of fit, our Anderson-Darling p-value is not less than 0.05, so the females have a normally distributed score distribution, and the males seem to as well. So we're good to go. That's pretty much it. Next time, tune in and I'll show you some more statistics. Thank you. Have a good day.